Okay, that's great.
So we have one professor from aerospace and mechanical engineering, and Mark from physics department is joining right now.
That's great.
Hello, Mark. Thank you for joining.
Pleasure.
Hello.
Is it possible to come in person or
Yes, yes, absolutely. It's actually in
where is it?
CCSB in the room number 1.410, 410.
1.4. I think I'll just walk over.
Okay.
Thank you. Well, maybe not. I suppose I'll miss the first part if I walk over. I'll stay here.
So how is the weather over there?
It's not too bad actually right now. It's not
Yeah.
on fire.
You're joking with me? Yeah.
It's a joke. So Alireza is
Yeah.
living in LA, so there was a big fire in LA. So it's a sad joke. I'm sorry.
Yeah. No worries. That's okay. We survived. That's a good part.
Anyway, so let's probably start. I'm going to turn the screen. So let's welcome Alireza, Dr. Alireza Shabani. Actually, is the person who got me started with quantum research. I got to know him and working with him when I was at Cisco. He was my manager and the director of the inaugural Cisco Quantum Lab. Alireza is an entrepreneur and a scientist of multiple startups. Right now, he is a co-founder of Entangle Space Incorporation, which is a startup company worked on satellite quantum communication. He previously established a quantum networking and security lab for Cisco Systems. He was also a senior scientist at Google Quantum AI Lab. He holds a PhD in electrical engineering from the University of Southern California and was a postdoctoral scholar at Princeton University and UC Berkeley. With that, let's welcome Alireza in this, and thank you very much again for your time for this guest lecture. Take it away.
Sure. Thank you, Saider, for inviting me, and hello, everybody. I think you can see all the students and those who are online. Yeah, I prepared some slides for as a like introduction about quantum networking and quantum internet, means a global quantum network. Yeah, so I look at what you have learned so far, and this is a more like an very high level definitions. So probably only on 3 slides I have some equations. It's more like you for a first time, maybe if it is your first time, you hear the concepts and that motivates you to go and follow to look for the more details. Let me share my slides. Okay. Do you have it?
Yes.
Okay, great. Yeah, just feel free to stop me. This is doesn't mean to be like an formal talk. This is a lecture, so ask your questions. If I can answer, I will help. Yeah, I'm also have an affiliation with the Center for Quantum Networks. It's a NSF center based University of Arizona and MIT. And yeah, so let's go through the first concepts. Before we get to the quantum networking part, I would love to. I have this a slide that I show. I mean, I start my presentation sometimes with this. This is very high level of quantum technology, pillars of quantum technology. So we are at the age, you hear quantum a lot in the news, quantum computing and different things. So we're at the age of the quantum engineering. Basically, we are able to engineer quantum physics systems and to basically to use them for information processing. So information processing can be computing, communication, security, and or sensing. Yeah, so and then these are basically the 4 pillars of quantum technology: quantum computing, quantum networking, quantum cryptography, and quantum sensing. Quantum networking sits in the middle now because it helps with quantum computers. It enables quantum cryptography protocols. I think you will learn about QKD, quantum key distribution, and also it helps with the quantum sensing. So maybe 5 years ago, quantum networking was not that critical, especially on the computing side, but now we see it's going to play a more central role in developing larger scale quantum computers. So it's, I think, we're going to see more development on quantum networking, which is a topic of this very high level presentation. And the other term is quantum communication. We exchangeably use these 2 terms. So you have learned about what is a qubit, right? We take some quantum system, we either is a 2 level, so we use it as a qubit, we define 0 and 1, or if it is more than 2 level, we take lowest 2 energy levels and that becomes a qubit. But in the case of communication, it's different from computing. Different in a sense that for quantum computing, you have different physical modalities. You can use electric circuit like superconducting circuit to build qubits. You can use atoms. You can use, optics, photonics. But when it comes to communication, we're limited to one item. I mean, one modality. That's the electromagnetic waves. So because we want our qubits to be able to travel, right? So in that regard, it's a bit simpler than quantum computing. We don't have those many variations. And yeah, so the workhorse of quantum communication are like photonic qubits, and primarily the optical or telecom domain. There are some proposal to build qubits in microwave regime or RF, but the RF problem is that it's very noisy. So literally they cannot live for more than a few meters. The signal dies. So we are limited to basically optical qubit to build our quantum communication systems. So qubit basically is defined again based off like a 2 levels, 2 state of electromagnetic wave. There are different ways to define a qubit. If you have some physics background, or I'm sure we have taken some basic physics courses. So, a traveling wave of electromagnetic, it has different degrees of freedom. The amplitude of that, can use the amplitude to define, 0 and 1. One other degree of freedom, which is very popular for quantum communication, is the polarization. And again, polarization that we consider is usually, we can have a vertical oscillation of the electromagnetic wave or horizontal oscillation. So we use these 2 states. We define 0 and 1 if it is, in this picture I borrowed from internet. A horizontal mode means 0, and if it's like a vertical, it becomes 1. So that's how we have a qubit that can travel. There are other ways to define 2 qubits. A 2-level system with the photons. We have circular polarization. I don't want to go through that details, but just keep in mind when we talk about quantum networking communication, we are dealing with optical qubits. Yeah, and I don't see the audience. If anytime there is a question, let me know. Someone should let me know. So what is a quantum network? At the physical layer, quantum networks are basically an optical network. So in today's world with the internet, yes, question? Okay, so no question. Okay, so yeah, quantum network is about having an optical network. And basically, that's what we have today, right? I mean, with the internet, we have fiber optics comes to our home if we have a high-speed internet, or even the backbone of internet. Or probably have seen this image of there are this huge wires of optical fibers that are laid on, they're under the ocean. And yeah, so basically fibers are one platform, that we use to build quantum networks. The other platform for optical communication is just free space, right? You can shine a laser, from one building to another one. Or in particular, what is hot now in the internet world is a Starlink, right? So Starlink satellites, they're a new generation. I'm talking about the SpaceX, Elon Musk Starlink system of satellites. Their new generation are equipped with satellite-to-satellite laser communication. So we already have a kind of substrate of optical systems. So we're going to use the same for quantum. The difference from classical to quantum is that classical systems, the signals are very strong. And then when we talk about the quantum optics or we build quantum networks, then we are dealing with the single photons. Just for comparison, the internet, now I'm talking to you guys, and my information from me to your classroom goes through lots of fiber, optical fiber. Typically, the current of the optics in those fibers are around 10,000 to 10,000 photons per second. So if you just to have that number in mind, and if I want to do a quantum communication with you guys, we are going from 1,000 to 10,000 photons to single photons limit. So systems are very, very sensitive, as you can imagine. Single photon can be easily lost. Yeah, and anyway, so when we talk about quantum network communication, we are talking about the optical networking. And this is a very simple cartoon of, okay, we want to build this network. It can be fibers, it can be free space optics, building to building, or through the satellite. The nodes of this network would be, depends on the application. Maybe you want to connect quantum computers to this quantum internet. It can be optical clocks if we are interested to look at application for time synchronization, the type of things that we use for GPS, basically. It can be for quantum cryptography equipment, for QKD, quantum key distribution. We need an optical network. We need the quantum networks to develop a larger scale QKD system. And yeah, so the core of quantum networking or quantum internet is basically how we want to build such a network, as we did before for an internet, right? Digital internet started in or classical internet, the current internet that we use. It was started with some DARPA project in 60s and continued in 70s, and then now is a kind of, we have all the standards well developed. We are kind of with quantum internet, we are in the 60s. So very first steps we are taking to define what we want to build, what protocol we have to use. And that's exactly good time as a student. So if you want to get engaged to come to this field. Okay, so why we want to build such a network? Okay, it sounds something cool, sounds scientifically cool to send photons, single qubits over long distances, but why? And so we're pursuing a number of applications that we know, and hopefully over the time we're going to find more applications. One is that distributed quantum computing. This is especially important for short distance quantum networks. So the story of quantum computing, yes. Question? Oh, okay. Quantum computers. So we need Right now, okay, so the quantum computers are different platform, different companies or research labs are working on that. We are at the stage of, 200, 250 qubits. That's maybe the largest with neutral atoms. But to do interesting stuff with quantum computers, we need to get to millions. So there's a huge gap. And except superconducting, maybe with superconducting, we can do a single chip of superconducting up to 1 million qubit. Maybe, probably not. But any other system like ions, or trap neutral atoms, other systems, a single processor cannot go beyond few hundred, maybe 100, 200. And beyond that, we need to connect this quantum processor, smaller quantum processors, through a form of network. Here, I just borrowed some picture from internet, but this is a problem. How we can build this quantum, basically we need a quantum network, and how to design a quantum network to connect this smaller quantum processor. So one application of quantum networks is distributed quantum computing. Here we are talking about, it's called local area network, campus network, short distances, few meters, right? There are other applications, quantum cryptography broadly, specifically QKD systems. That's exactly, we literally need quantum network at all the different scales. Short distance, local area network, metropolitan area network, and eventually global networks, right? That's other whole paradigm of application of why we are building quantum networks. Related to quantum computing, there is a totally different applications that we need line distance communication. Imagine we build quantum computers, right? There are different companies working on building quantum computers. There is a particular application called blind quantum computing or privacy preserving quantum computing. If you imagine that quantum computer is connected to quantum internet, means, I'm sitting in LA, I'm connecting to the IBM quantum computer in New York through some sort of fibers or satellite communication, right? So I can communicate single photons between LA and New York. Then I can run blind quantum computing is about, I can run some computation on an IBM machine in a private manner. Means that the provider of the computer, which is a company of IBM, they cannot detect what calculation I'm doing. So it's called blind quantum computing. It's the same concept as privacy preserving computing, more in the classical world. And this is, for example, an application of quantum networking for quantum computing, which actually we do need line distance communication. The other applications I put here is more scientific oriented. It's called line-based line telescopes. The idea is that, if you have a single telescope, it has a certain power of detection of the, image and lights that come from a sky, the deepest sky. And if that image that comes from deepest sky is very weak, okay, a single telescope has trouble to detect that. But there are proposals that if you have a number of telescopes, with distance of like 10 kilometers or 100 kilometers, if these telescopes are connected through quantum network, means they can exchange photons between each other, then the whole thing becomes much more powerful. You have a number of telescopes connected, then you can detect much bigger signals than a single telescopes. And there's more to this. I just put some of the main applications. So this is why you want to build a quantum network and eventually a quantum internet. And what is this quantum internet? I keep using this phrase. There are different definitions for that, but then people say, okay, it's a network of quantum networks. This is very similar to what we call the digital internet. We call network of networks, or simply maybe something more practical, at least the first version we are thinking of that, building a global quantum network. Means we will be able to exchange photons or single qubits between any 2 points on the globe. So if we have that, then we call that we have a quantum internet. This is the image from Chinese quantum internet testbed that they have. For some historical reason, Chinese are ahead in developing their quantum internet technology compared to, in particular, US. Europeans are doing good too, where US is kind of behind. And yeah, so they have a network of both fibers and also satellite communications. Yeah, so I can't remember exact numbers. Probably overall, we're talking about 3,000 to 4,000 kilometer, the whole connection. And they're running some quantum key distribution and other application on top of their platform. So yeah, quantum internet is basically global quantum network. Before I go to the more, fundamental definition of is that there is a difference between when we talk about quantum network than the digital internet. Quantum internet versus the digital internet. By digital internet, I mean the internet that we use for classical internet. So the internet that we have now is basically a network to transfer information, right? So I'm talking to you guys, my voice will translate into bits, and those bits of information is sent to you guys so you can hear me. The same is for videos, for bank transaction, everything, right? So it's a network for transfer of data, information. And you maybe think, oh, so quantum internet is the same. Actually, quantum internet 2.0, the future of quantum internet is going to be something like that. Basically, we build a network so we can send classical or quantum data over the internet. But there is a step before that. That's in building a network. I put two cases, version A and version B. You can call it 1.0, 2.0. What we are trying to build now is not that network that transfer information. The reason is that that's very, very challenging. Again, so the noise is the main problem. We have a problem of photon loss. We cannot go to long distances. Eventually, we want to get there. Eventually, we want to have a network so we can send our qubits of information over the network. But that's technologically more challenging for future. Right now, the efforts are build a network to distribute entanglement. And what does it mean? I want to start rest of my presentation to talk about, basically most of my presentation would be around quantum internet, the definition A. Quantum internet is a network for distributed entanglement. I hope by now you have learned about an entanglement, right? Because I thought you, yeah, I saw your, at least from your course material that you have learned about APR pairs and that kind of things. So just to remind you, what is entanglement? Entanglement is about basically two qubits. It can be multi, but the simplest case, we have two qubits that they have this spatial correlations. In this picture, it shows we have two agent or two player, Alice and Bob. They are far distance each other, thousands of miles, and we want to basically send entanglement, generate entanglement, and send one of the photons to Alice and the other one to the Bob. How does this work? Again, this is a very simple cartoon of actual physics that happens. The box, it's their colorless box. Basically, you take a crystal, a nonlinear crystal, and you shine a laser to that. And because of this nonlinearity effect that it has, it generates a lot of different photons and at different frequencies. But one particular photons that come out of this nonlinearity is that we get pair of photons, two photons, which their state can be described as an entangled state. The simplest is 0, 0 plus 1, 1. And the concept of entanglement distribution is literally we generate that entanglement somewhere in the middle, and we send one photon to Alex and one photon to Bob. Why we want to do that? Because entanglement is a resource for a number of the quantum protocols. Just have in mind that entanglement by itself, that state 0, 0 plus 1, 1, it carries no information. It's an entropy 0. It carries no information. It's just a resource, right? If Alice and Bob have that, they can do lots of interesting things. So in that regard, the first quantum Ethernet kind of platform that people are trying to build is not a network to transfer quantum information or any type of information. It's a network just to distribute entanglement. So in a sense, it's more like we're building a electricity grid, a new electricity grid, because electricity is a resource that when you have that, you can use it in different ways. Similarly, we are building a network to distribute entanglement. It's a resource for different applications. And yeah, so what are those applications? Again, this is, so so again, I just putting some of the main applications and much broader than this. One application is QKD. So you have learned about QKD BB84 protocol. It's called also prepare and measure, that Alice prepared this from what you learned, prepared, these states, in two different non-orthogonal bases. It communicates with Bob, and they can extract keys. There is a more advanced version of QKD, is based off entanglement. If Alice and Bob, they have shared entanglement, again, similar to the previous slide, there is some source of entangled photons. One of the photons goes to Alice, one of them goes to Bob. Then that's the resource they have. They can start using that, running some protocol, and extract keys. So it's called entanglement-based QKD. And the advantage of that compared to what you learned before BB84 is that it's device independent. It's more secure than what you have seen before. So this is one of the applications of the building a quantum Ethernet, just to do a secure communication, with device independent QKD. The other applications I talk about, distributed quantum computing. If you build a network short distances, so all the proposal or most of the proposal for distributed quantum computing requires a network to distribute entanglement between different quantum processors. Quantum processor 1, quantum processor 2, if they have some entanglement shared between them, they can, do some remote or teleported gating. So in that regard, we can have a distributed computing. So that's another application of building a network for entanglement distribution. One topic, quantum teleportation. I don't know if you have learned about that so far in your course or not. I don't want to go through that. It takes a whole few slides to talk about what's teleportation. But if not, so I think it's good after a class to go and learn if you already don't know what is teleportation. But the idea is that if Alice and Bob, they have a shared entanglement between them at any distance, then Alice Bob, they can start doing some communication and doing some local measurement on their photons. And the end of the protocols, Alice can teleport, or basically can copy the qubit. So here, okay, this protocols, Bob has 1 qubit, Alice has 2 qubits. One of the qubits is shared with Bob for entanglement, but Alice has this other data qubit X that wants to send to Bob. And through this quantum teleportation, basically the qubit information of the Alice X will be copied into Bob's single qubit that it has. So quantum teleportation is about sending quantum information or without actual physically sending that through a fiber or some physical media. There's something unique to quantum. And for this teleportation, you need entanglement as a resource between any two parties want to communicate. And the other applications, I told you about this telescope concept, connecting many telescopes, and if they share entanglement between them. This is, the whole concept is broader than just telescopes. Basically, any type of sensor that you have, you can connect them through some network, basically, that, you know, if there's entanglement distributed between these sensors, they can become much more powerful in their sensing task. It doesn't need to be imaging, it can be any type of sensing. For example, there are proposals to have RF, you know, building new radars, quantum radars, when your RF, basically the receivers are connected through some quantum networking, so you get a much more powerful RF array. And again, so some applications specifically why we want to distribute entanglement. Sorry, have some water. Yeah. And then now the question is that how we want to, let's go back to the physics, how we want to build this network. I told you we have two options. Either we send photons through fiber or free space and satellite. Both of these directions are being under development. This is a map from the test bed, you know, being developed at New York area between different universities, national labs, and some company involved. And yeah, so it's around like 100-kilometer big loop. And so this 4 or 5 different nodes are connected through this fibers. And so the nodes, in what it has, there are a number of the entangled source, so source of entangled photons there. There are a number of the measurement devices, because you have to measure and detect some of the photons that you have. Quantum memory, I don't want to go through all the details, and there's lots of, it's experimentally complicated system to be developed. What is challenging is about fibers is that the loss is very strong, relatively strong, isn't, and it's exponential. Means like with the distance, the loss of the photons, or chance of loss of photons is goes exponentially down. So with the current fiber technology, we are talking about a 0.25 to 0.35 dB per kilometer. The conclusion is that with fiber, you cannot go beyond, 10 kilometer, really. It's good for metropolitan area to build network. Beyond that, it's a challenge. How do you want to, with fiber, how do you want to go beyond 10 kilometer? I'll get to that. So how we are trying to address building quantum Ethernet line distance with fibers. The other paradigm, which is more realistic with the current technology that we have, is doing communication with satellites. Just the basic concept of satellites. So satellites are the objects that are traveling above the atmosphere. So think about, we have Earth, there's atmosphere above that, which is kind of very lossy, because if you send the photons or light through atmosphere, it gets absorbed. We are talking about, okay, there are different numbers, but around up to 20 to 30 kilometers above the atmosphere, above the ground, there are like this heavy layer of atmosphere that we lose photons. But above that is almost vacuum. I think the correct number, exact number is 80 kilometers, but is it get diluted if you go beyond 20 kilometers. So really, where the satellites are traveling, for example, a Starlink satellite, is almost vacuum. So if you send the photons from one satellite to another one, almost there is no loss from the absorption. There is loss because you get your signal is a wave, right? It goes, the cross section of the signal goes quadratically becomes larger and larger as it travels with distance. But it's a quadratic, with fiber, we had exponential loss with distance. With a satellite, between satellites above the atmosphere, you get quadratic. So this gives you an idea is that, okay, so satellites is a way to go if you want to have a long distance communication. You may ask, okay, what about the loss through, if you want to, okay, from satellite to the ground or ground to the satellite, we're going to have loss. Atmosphere absorb photons, so we have loss. It's also exponential, but means if the photons travel more and more into the atmosphere, it gets exponentially decayed. But the trick is that with satellite, we can, if we prepare, properly design our satellite network, and if we shoot the signal photons from the satellite to the ground, when it is more or less above our detectors, then I don't know if you can see my mouse or not, but sorry. If we can just go, imagine we have a satellite and we just orthogonally, or vertically, we shoot a photon down to the ground. So in that case, photons will travel kind of a fixed distance into the atmosphere, like 20 kilometers. So there'll be fixed loss around 10 dB. Okay, we're going to live with that, but that's fixed. And then if we do the rest of communication of the photons above the atmosphere between the satellites, so we can go much, much further distances compared to if you want to do everything on the ground. And roughly, if we say, okay, with the photon, we can go 10 kilometers. With the satellite, you can do 1,000 kilometers. I mean, you have to define the right metric to make a comparison, but just a very ballparky way to think about that. So satellite is a one very practical way to go long distance communication and build a kind of at least the backbone of the quantum Ethernet. Just let me know if there is no questions. Can not, I can continue.
So I have some questions.
Please.
It is already been on the chat.
Oh, sorry, I cannot read the chat. And yeah, someone should read those. Let's see, where did I define values? Okay, sorry, we had a couple of questions. Atomic clock and optical clocks, what are the differences? So, atomic clock or atomic based off the atomic resonance. So you can do some research, but if you take, atoms are kind of very well defined, very stable systems, means their two-level systems are kind of fixed the energy level to the high precision, and atoms of the same elements are very similar. We don't, we take two atoms of cesium to a very high precision that we can measure, the energy levels are the same. So they make a good clocks if we can try to read the oscillation between the two levels or multiple levels that they have. Optical clock, well, I don't know if that was on my slide. It has different definition. Some atomic clock that operate in optical regime. Some of the atomic clock, they operate in the microwave. Some of them are optical regime. It's called optical clock. And we do have optical clock they have nothing to do with atomic. They are just based off the, precision of the entanglement. So I don't want to go through that, but most of the time when you hear optical clock is basically atomic clock that operate in optical regime. The other question was, what is the physical meaning of A and B in the picture of entanglement? That was our Alice and Bob picture. I don't know which gentleman, Arif.
Yeah.
You mean in this picture?
Right.
Well, they have no physical I mean, the physical meaning there are two users. They can be human users with some equipments. They can, they have memory. They can take the photons and store that, or they can be just devices, some QK devices. Basically, two nodes. The photons arrive, and the photons can be consumed for some protocol, or can be stored in a quantum memory for the future use.
That means actually the picture you mentioned, the 0A and 0B means two nodes.
Sorry, there was an echo. Can you ask me? Hello? Or if someone, I don't know if you're in the room, if someone else can ask that question. Does it mean two? Yeah, yes, exactly. Two nodes. It's a simplest network, right? One line and two nodes. Thanks. Yeah. Okay, thanks. Let me go through my next slide. I don't know how much time we have. I think I'm going to take the whole many slides to go faster. But I mean, can stop me anytime. So, yeah. So we learned about there are two paradigm to build internet network: fiber and free space optics. And slide. Okay, so and the quantum Ethernet is about, and that's under development. There is no final design for that. We are talking about a hybrid network of the fibers connecting buildings together. Satellite we talked about, but also some groups are looking at the free space with drones or balloons or any planes. So not going all the way to satellite, trying to look at the midway solutions. So how does it look like quantum Ethernet? We don't know yet. We're under development, and you can do lots of researchy work here. Let me go to I keep losing the slide. I apologize. Okay. So far I talked about the current idea around developing quantum Ethernet, which is basically developing a network for entanglement distribution. But as I told you, eventually we're going to go toward the more toward what the idea that we have around the internet, basically having a network to transfer information, the actual data, right, over the network. Alice and Bob, they want to communicate. Bob wants to store the information on a qubit and send it to Alice, right, without teleporting, without anything, just directly sending information through the fiber or satellite to Alice. This is much more challenging because of the loss, everything you heard about. And this requires a quantum computer, basically. Every few kilometers, we install a quantum computer to do error correction, to correct the errors for loss and other type of errors. So you can think it's as hard as building a quantum computer. But already there are lots of research been done, especially in the CS, more abstract world of the quantum cryptography. The whole area of and quantum cryptography is much beyond QKD only. QKD is a one paradigm for quantum cryptography. There are ideas around quantum money, yeah. Imagine there's a money, but with quantum systems. So it's much more secure. I send money to Cider, and then, but I do it through you guys, but I do it through some quantum communication channel, so we can nobody can copy that. Or quantum copyright. There are lots of ideas around, using quantum systems for different quantum cryptography protocols, and they all goes to what's called the quantum system are not clonable. Means that you cannot copy a quantum system. You cannot without disturbing them. So it's a more fundamental idea around that. Again, so I have just one slide about this quantum internet as a like an really actual network for data transferring data, because that's much more challenging to build. But again, so they're a very interesting area of research in computer science. So you can look into that. The rest of my presentation, I talk about some of the main challenges that we are dealing with to realize quantum networks and quantum internet. I'll go back to the challenge of distance. So the whole line distance communication is challenging. Fiber is lossy, satellite is much better, but even with the single satellite, you cannot build a global network. Around like 1,000, 2,000 kilometers, the signal dies. So what you want to do beyond that? So that's the one big problem here. And one solution to that is the different solution. One of them that is a topic of research is the idea of the quantum repeater. And what is a quantum repeater? Next few slides, I want to be more like an actual teaching you some actual quantum protocol. Quantum repeater is basically a quantum computer. I just talked about that a few minutes ago. It's a quantum computer that for error correction. The simplest idea of the quantum repeater in the next 3 or 4 slides, I want to talk about that. Again, so it's going to be very fast. We don't have time to go through all the equations, but this can be a good starting point if you want to go back and work out the details, so you're seeing how things work. So what's the idea? The idea is that, okay, we want to send a pair of photons to very long distances, kind of arbitrary distances. How to do that with these lossless systems that we have? I start with 2 points. Suppose we have 2 points, A and B, with a distance 2L. How we can assume 2L is too large to send a single photon. Suppose, let's put like L is like a 10 kilometer, then 20 kilometer, we have no signal. But in 10 kilometer, we have some signal. So we cannot directly send photons between Alice and Bob, A and B, but somehow through this trick I'm going to walk you through is that we can distribute entanglement between these two parties. Suppose Alice is equipped with the source of entangled photons, that crystal that I showed you. This is basically it's a source that generates pairs of photons which are entangled. And Alice also has a quantum memory, so Alice can store one photon. Imagine the same is for Bob. The protocol works like that. Alice generates pairs of photons, stores one of them in the memory, sends the other one through some fiber or other medium to the middle point C. Bob does the same. Generate pair of photons, store one of them, sends the other one to the Charlie. Charlie sitting in the middle, waiting for these 2 photons to arrive. And Charlie has detectors. So what is detector? You have learned about quantum measurement, right? So you have some quantum system, you measure that in the different bases. So a detector is a photon detector. I mean, when the photon arrives, you detect either you get a click, photon has been detected or not. In that regard, you have project, you can see say is 0 or 1. Or if it's like a polarization, that's a different topic. So Charlie in the middle has this unique, well-designed measurement setup. It's called Bell-Ested measurement. I'll get through details of that. And then Alice, and then Charles, so Charles has 1 photon from each, 1 from Alice and 1 from Bob. And through some measurement that we're going to see in the next slide, it can virtually generate entanglement between Alice and Bob. So how does this work? These are some equations. Again, I don't want to go through the whole details of this. So we just take this slides, or you can find it online to work out the details. And mathematics is very, very interesting. This is basically, we have pair 1, generated by, so I'm kind of misusing the names here. I should change this slide. But the player I called Alice before on the left, let's see what they use. Yeah, Alice on the left, it creates photon A1, it stores that. It creates photon B1, it sends it to charge in the middle. And the Bob stores its own, one of the photons B2 and the A2 is sent to the middle. So basically these are different way to write entangled pairs, but this is a one version of that. And before these are arrived to the detector to be detector measured, this is the total state of Alice and Bob. So there are 4 qubits here. Pairs are entangled, but then Alice photons and Bob's photon are not correlated. They are separate state. So is it basically a tensor product between psi A1 B1 and psi A2 B2? If you take pair 1, pair 2 and expand, you arrive at this equation on the bottom. And now what's happened with that BSM, Bell state measurement, and what is the Bell state measurement? Bell state measurements are kind of projective measurements. Hopefully you already know these concepts, what does projective measurement means, but basically it's the measurement setup not for a single qubit, for 2 qubits. And it has 4 different outcomes. And whatever state that arrives at that Bell state measurement setup, it will be projected into one of these 4 states, phi plus, phi minus, psi plus, psi minus. And these are kind of projector operators. And depends on the state that we have arrives at that Bell state measurement setup, it will be projected to one of these with the probability that you can calculate from basic quantum mechanics rules. And in our case, the 4 qubits that arrive, basically, okay, 2 qubits here, B1 and A2, arrive at the Bell state measurement, and randomly they go through one of these 4 possible states. For example, if you assume we get click, it's a random process with some probability. If we get click that, for example, we project B1, 2 photons, B1, A2 in kind of entangled states phi plus. And if you again, so if you look at this 4 different possibility, all of them are entangled states. So 2 photons, B1 and A2, they are not entangled, right? B1 and A2 comes from totally separate sources, so they are not entangled. But after this measurement, they get entangled. And that's exactly what we want. So after we get 2 photons that are entangled, not entangled, they get entangled after this Bell state measurement, then effectively the effect of that projection is that the other 2 photons, which were stored locally, A1 and B2, they get entangled. So in this regard, in this way, Alice and Bob, they can create, they can have a pair of photons which are entangled over a line distance 2L, which was not achievable before because they couldn't go beyond L. So this is the simplest protocol called quantum repeater, and that's how we can double the distance of the distance that we can distribute entanglement. So then you can imagine this is a iterative processors to go to line distances. I don't want to go through that, but you can just play with the idea. We have again, so you can have multiple of these photons, multiple of these setups, and kind of in this hierarchical structure, we can go from 2L to distance 4L, 8L, and beyond. There are limitations to this. The limitation comes, of course, now there's no free lunch here. The limitation comes from the fact that the rate of entanglement generation, the entanglement is probabilistic process generation of that. And not only that, okay, there are versions that we can deterministically generate entangled pairs, but the outcome of that balanced measurement is probabilistic. So there is a trade-off here also, how far we can go, but doing some math, actually, we can go to arbitrary distances using this protocol. It just becomes a longer and longer time to go to long distances. So this is one way to go entire distribution long distances, and some people are trying to build this for fiber solutions specifically to go to very long distances. So this is the end of challenge 1, and I try to explain one solution here is long distance quantum communication or quantum networking. Challenge 2. Challenge 2 is that so we say kind of, if you look at from outside, is that, oh, you're using the same fiber that we use for classical internet. You're using also satellite laser communication, right? For classical. So the medium is the same for when you want to do quantum. So how we want to, one main question, if you want to build a quantum internet, how do you want to do that? Do you want to really build the whole infrastructure, all the fibers that we have, all the satellites, or you want to just use the same medium? So that's a kind of open question. There's no answer to that. Some people say, oh, why not just build, all the fibers again in all the cities and build a quantum internet? But some people say it's not economical. So we end up having with the challenge some people try to solve. It's called coexistence of quantum and classical. The literature on that, I put some of our paper when I was at Cisco. We work on this general definition of quantum internet. We try to answer these questions. But yeah, so the big challenge is that how we can basically use the same fiber to send quantum and classical signal, or the same fiber, or free space optics. If you want to do that, then we have to do some form of multiplexing, right? So if you have some engineering double background, you're familiar with this multiplexing idea, is that you can basically, we want to mix different signals in some form. Sometimes the multiplexing in time. For example, we send quantum data or some quantum qubits, and with some time delay, we send classical data. Or can do multiplexing in frequency or wavelengths. For example, one common idea is that, okay, let's send classical data at the frequency 1550, and then send the quantum data at different frequency 1310. These are all very well-established frequencies for telecommunication. There'll be challenges here. Is that, again, I told you that classical signals, the laser that goes through the fiber now, are very strong, 1,000 to 10,000 times stronger than single photon, so quantum signal. There are lots of interference, so it can easily kill your quantum data. And how we want to handle that? One solution would be, okay, let's run them at different frequencies. The bigger problem here is that the current internet that we have that works with fiber is they're not friendly with quantum signal. Why? Okay, fiber is fine. Maybe we can use the same fiber to send the quantum data qubits through the same fiber. But there are nodes, for example, AT&T, Verizon, they have switches here and there. And at that switches, with the current technology of optical communication, all the optics information signal turned into electronics to do error correction, to do routing, everything. And the electronics will be transferred back into optics. So, for example, I want to send data here to your city. For example, I send it here to, I'm just saying, to Arizona, maybe. But then the Arizona, this light data, this laser data, they turn into electronics. And then they do some correction of the data error correction, and they will be turned back into optical data and send it to you guys in Texas. This is not going to work with quantum because if you send photons, you cannot touch the quantum data, right? Quantum qubits. If you do any transformation on quantum, doing some measurement, you kill the quantumness. So that's a bigger challenge of the coexistence problem because at the nodes of the current design that we have, the quantum data need to be separated into something basically not transferred into electronics. So we need to at least, if we don't install a new fiber, we use the same fiber or satellite. But at these switch stations, we need to install quantum specifically routers and switches. And that's a whole different topic and lots of work people are doing to design that kind of routers. And this is challenge 2. And the last challenge is, when I say challenge, I mean these are area of the development. So lots of research needs to go through this. Is that we are in the early days of designing quantum internet protocols. So we don't have an ultimate solution here. Suppose you want to design some network for quantum key distribution for secure communication between a number of the local bank branches. So this is from my hometown in LA. I picked some, and that actually most of this map there was fire here, but yeah. So these are just some Bank of America branches, and you want to do QKD between these branches. Question: what kind of network we can design? So where do you want to put your photon sources, switches, routers, and protocols? So this is the area of the research that's being done. So we try to, again, just giving some example of the type of research. We try to address this problem for countrywide, I mean the US-wide network. In these publications, is that this shows some map of the current fiber optics for research on the west coast of the country and also on the east coast. And then we ask this question is that exactly we try to address this ask these questions that where we should locate put our photon sources. I mean, fiber is the same fiber. This testbed has been developed for classical internet. We want to use that for quantum, but where we want to put our photon source, where we want to put our detectors to build that quantum repeater protocol that I explained. And okay, we published something here, but just giving this an example of the protocols and the architecture design idea need to be developed until that we have an ultimate answer here. And it's not, and then this problem is not just limited to long distance quantum internet. I talked about the quantum computing. That's building a distributed quantum computing. That's a whole other area of the research, very active in the area of quantum computing, and many of the companies who work on quantum computers now, they're actively working to address this question. Is that okay? We told that we said that okay, we need millions of qubits. We cannot build a single quantum processors. If it's atomic systems, cannot go beyond like a few hundred, then we need to connect them through a large quantum network. And this quantum network is a short distance. We're talking about tens of meters or 10 meters. It's more like a supercomputing kind of networking. And so where do you want to put the switches and what are the ideas here? And there is no final answer. And we are just, maybe in the last 2 years, people have started thinking about this problem. We knew we need to connect quantum computers at the physical layer, but at the larger scale, design of the larger scale quantum computer is totally open. How we want to, design this network, what's the architecture, what's the protocol for entanglement distribution, and yeah, so you're really at the stage if you want to continue doing research or go into industry doing work. There are lots of interesting problems here to be be addressed, and hopefully we can contribute. So let me stop here and answer your questions. There are some more
If
questions.
you guys have any questions, you can probably come up so that they can, whatever we can probably shout out the question. I think we have some question in the chat. The chat box, yes.
Yeah, okay. The questions, okay, let me see. Who knows? Based on the satellite to satellite communication, should the optical alignment be highly accurate? How big challenge is that? Yeah, of course, it's a challenge. Our current estimate is that we don't need something beyond the accuracy, a little like that. So right now we do laser communication, satellite laser communication, right? With the same precision, the technology available there for classical laser communication, we can use that with the quantum and still get a good signal. Of course, higher precision helps, but the current technology for satellite to satellite laser comm is enough to build kind of early version of the quantum internet. So, and then next question, classical means electromagnetic RF communication signal currently widely used for current antenna. Classical means classical signal, means like many photons. So it's but yeah, okay. So yeah, basically the current internet and that we have. That's what classical means that.
So I have a question. So right now we are working on some of the projects on the satellite and trying to see if we can. So the like the research that you have shown that people have used instead of satellite, maybe some drones to do some sort of experiments. So
Yes.
my question is, well, in terms of the satellite communications, right? So what can we do in terms, is it going to be version 2 of the Starlink kind of satellite internet, or it can be like you mentioned about entanglement. Right now, the quantum networks is basically people are working on entanglement distributions, right? So is it going to be satellite? Is it primarily investigated to distribute entanglement, or we can also think about to kind of build a satellite internet?
Both basically. Yeah, you can use that for entanglement distribution. You can simply put the source of entangled photons on the satellite and shoot down the 2 photons to the ground for entanglement distribution. And yeah, eventually, if you want to use the actual internet to communicate quantum, any type of information, yes, then in that regard, you need both ground to satellite and also satellite to the ground communication. So because it needs to go through network. So yeah, both are underdeveloped. Well, probably primarily the first step again is to do entanglement distribution before going to the full data transfer.
Thank you very much. So I have actually a follow-up question. So you mentioned like shooting the laser, right, from the satellite to the ground station.
Yes.
Now, one of the pressing challenges to see how do we align this kind of receiver and the transmitter. So actually it's a two-part question. First one is how can we kind of address this challenge or question, and second one is what would be the good resources to actually look into this problem, the alignment problem.
Yeah, so that was the other similar question. So it's on the classical laser comm for classical signals, there are lots of development, lots of technique. For example, the most advanced is called adaptive optics. So yeah, it's we can just borrow the same technology and use that for quantum to get some signal. But again, that's a big challenge, not just for quantum, even for classical laser communication, you have to deal with the same problem. But it's the lots of development happening in the classical world that we can borrow that for quantum, basically.
Sounds good. Thank you.
Yeah,
So there are 3 questions for you in the chat.
Yes. What are the list of components, devices we need to simulate satellite-to-satellite communication on the ground? You mean simulating, writing a simulator, or what does it mean? I didn't get the. Is a question about simulating that process, like writing a code to simulate?
Basically, what I like to know, if we like to simulate satellite to satellite communication in ground, do some experiment and check the result, will it simulate the space environment?
You mean, do you mean maybe emulate, right? Using
Maybe,
building
yeah.
an emulator to mimic the same. Well, basically, I mean, many pieces can be tested here, right? So I've seen people, what they do is that, well, you can, okay, depends on the distance, but for example, that adaptive optics technology you have, you can design that and then test it on the ground. So you have free space optics, for example, on the campus network, you can build it on your campus, or even if you want to mimic the moving part of the satellite, you can take some drone or take some track and put your detectors on the track, and track goes. I think I calculated once, if we can install some source and put your detector on the track. I don't know how correct is on my mind, but if they are like a mile apart and the track goes like 60 kilometer or was like 1 mile was 60 miles per hour, then it's almost the same distance having like an satellite traveling over 500 kilometer distance and then trying to communicate to the ground. So well, you can do that kind of emulations. Actually, it's not just a static, because one part of emulation is sending signal to atmosphere, but the other big challenge is that trying to lock your transmitter to the ground station, to optical detectors, by putting one of these on a track and then go fast and then trying to emulate that behavior on the ground. So these are the way you can test things on the ground. Did I answer your question?
Yes, thank you. And there is another one.
And there's okay. If we simulate bulb endless communication in a high vacuum chamber, will it be acceptable? Yes. You mean this is for what purpose? To simulate the satellite to satellite link? Yes. Is that, you mean like, is it? Okay. Yeah, of course, right. So you can simulate that. So that part is, but again, so I think that the big challenge is that the satellites are fast moving objects. Again, even for Starlink, there are these whole challenges. I think if you want to connect the satellite that they go in the same orbit, okay, they're relatively static. They're not, they're not moving relative to each other. But if you are making laser link, and these are the challenge for classical laser link between the satellite or going into different orbits, then that's a much more challenging work. I think the current version of the Starlink is okay. I'm not sure. I thought it's only they're connecting satellite in the same orbit, but maybe I'm wrong. Yeah, but again, so you can do things in the chamber. That's the simplest thing. But if you make them move, then you have the actual full emulation behavior, which is hard with having a chamber and making them move. But yeah. Okay. Question?
Any questions from students?
So yeah, hopefully that has been motivating for you. And yeah, you can just follow these ideas and then read more papers, and hopefully you find them interesting.
Thank you very much, Alireza. It was really a very good lecture. I really enjoyed it, and there are lots of information.
Okay.
Would you be kind to share the slides for the students?
Yes, I will. Yeah.
Thank you very much.
Okay.
So
Thank
let's
you very
thank Alireza again for the very nice lecture.
Sure. Thank you, and good luck with your coursework.
Thank you very much.
Thank you, Saider. Okay, have a good day.
Talk to you soon. Bye.
Bye.